Computing within limits is a research field that investigates how computing can operate sustainably within planetary, ecological, and resource boundaries. It challenges the assumption that current trajectories of ever-increasing production and consumption will continue indefinitely, recognizing that humanity faces fundamental planetary constraints related to climate systems, materials, and biocapacity. A practical example of computing within limits is found in low-power hardware design. Engineers are creating devices that meet essential computing needs while minimizing energy consumption. These systems prioritize longevity, repairability, and minimal resource use over processing power or feature growth. For instance, some organizations develop modular computers where individual components can be replaced rather than discarding entire devices, extending useful lifespans while reducing electronic waste and raw material extraction requirements. Computing within limits connects to several critical areas. It aligns with efforts to create sustainable infrastructure that prioritizes long-term ecological balance over short-term productivity gains. It directly addresses issues of material scarcity by rethinking how we design, manufacture, and dispose of electronics. Most importantly, it questions the default assumption in most computing research that ongoing economic growth is both achievable and desirable. Recognizing that this worldview conflicts with evidence from many scientific fields showing planetary boundaries that must not be crossed. Examining post-disaster scenarios provides insights into computing within limits. After Hurricane Maria devastated Puerto Rico's infrastructure in 2017, communities developed improvised, resilient communication systems using minimal resources. Local technology experts established low-power mesh networks to reconnect neighborhoods when centralized systems failed. These adaptations arose not from abundance, but from necessity, illustrating how computing can function effectively when resources are constrained. Such examples demonstrate that innovation often flourishes, not despite limitations, but because of them, as communities develop solutions appropriate to their actual circumstances, rather than assuming unlimited resources. Computing within limits connects with social and biological systems in several profound ways. It resonates with steady-state economics, which emphasizes qualitative development without quantitative growth, similar to how Earth's ecosystems develop without physically expanding. It relates to urban planning practices that optimize resource flows while creating livable communities rather than emphasizing endless expansion. It informs education about computing by encouraging critical thinking about the full lifecycle impacts of technology rather than focusing solely on capability advancement. Each of these connections demonstrates that computing exists within nested systems of ecology, society, and economy rather than separate from them.